Anyway, it doesn't work. Yes, of course. Yes. You know. Thank you. So this talk is a continuation of what I said yesterday about this tool of child drawing, dessin d'enfant in French, that was created by Grothendieck, French mathematician, that died last year. And yesterday I've shown that you start from the three groups from two generators. Then you take subgroup of it, of a finite index. And behind such a choice of a group and a subgroup, there is a Coset table. And the action of the generator leads to a pair of permutation groups. That is precisely a child drawing, a dessin d'enfant. And the child drawing is a graph with black points, white points, spaces. It has topological properties. It has algebraic properties. And it's also able to stabilize finite geometry that may be relevant for quantum mechanics. So I'll show you a few applications of this method, mainly in mind quantum information physics. But I don't only concentrate on simple geometry. I want to show you that we can access quite sophisticated geometry. I gave a few examples yesterday. Some polygons, some near polygons. But I would like to show you how to use the tool. Taking into account that there exist dictionaries. And what that have to do with what I'm talking about. And the first dictionary is this one. Now, the first dictionary is this one, so-called Atlas for Finite Group Representation. Here you have the address on the internet, and it includes finite representations of many groups that are classified as so-called classical groups, like symplectic groups, unitary groups, orthogonal groups, linear groups, and so on. These groups may have an infinite number of elements. And there are also the so-called sporadic groups that are strange exotic series that correspond to groups of a limited size. But the biggest one is the monster group, which is quite huge, as I will show at the end. So, in this atlas of finite group representation, you have the representation of the group in terms, most of the time, you have the representation of the group in terms of two generators. So that it's precisely what I need, two generators. Because as soon as I have a group with two generators, two permutations, the generators are permutation, then it can be considered as a child growing, descendant form. But it's a bit strange that it was not used before. But this link between this representation and this finite representation with two generators and the methodology I'm talking about. So this is the first dictionary. And now if you have in mind a spectra of graphs, like we have in mind graphs or geometry, there is this dictionary about the most graphs of small size, you see, up to 1030, 500, that will be correspond to my index of the subgroup, okay? And another one is a list of generalized polygon on small order. So, just to show you how, but if you have internet you can check, how it looks like in the atlas finite group representation. You have, for example, all these classical groups, and you have symplectic groups, list of symplectic groups, you see the list, unitary groups, and so on. So I will go back to this list, for example, the list of symplectic groups. But I remind you what I said yesterday. You have this free group. You have a subgroup H in G, a partition in pieces, the number of pieces that is the index of H in G, and you create, by this way you create a Coset table, and under the action of the word N and B, you get two generator permutation group that has nice topological properties. I said that was allowing us to have coordinates of the discharge rowing associated to two permutation groups in terms of representative of cosets. I also said that one can create a geometry and one can check if on two edges of the graph on the cosets are the same. To define contextuality. For this slide, but now I'm specializing on symplectic aspects. Remember the first day I was talking about what are the commutation relation of multiple qubits, 2 qubits, 3 qubits, and so on, multiple qubits in general, that may be 2 qubits, 3 qubits, and so on. And I said a few things. And if you remember, I said that the geometry of the observable of multiple qubits was that of a symplectic polar space. And it was the number of elements of this symplectic polar space that could also seen as a sum of divisors of this. But this aspect of sum of divisor is not so important. Remember that there is now we have a space of quantum observables that is quite well characterized in terms of the geometry for the symplectic polar space. And behind this geometry, there are the symplectic groups. Okay? So one starts from a vector space, and one arrives at a symplectic polar space. So, and there are elements of this geometry that have to do with Newtonian biphasors and to maximum commuting set. Not necessary to understand everything, just remind that we have everything to talk about these spaces of observables. So, now I'm trying to use this tool of descendant form, strike drawing, to approach the subject. So I know now that we have these symplectic polar spaces that are talking about the multiple qubits. Not a simple task. So, and now I'm using the atlas of finite group representation to get the geometry straight away. For example, remember these are my symplectic groups. I take this simple case. Symplectic group for 2, what is just the derived subgroup. So I take this simplest case, and if you look at the atlas of finite group representation for this entry, you find a few things. You find the G. In fact, the G is not only the free group; it's already in the G. There are already a few relations. One involution, the second element should be of order 7, and there are extra relations. And they give a list of subgroup H of finite index, and I take this one in the table H, the one of index 63. I didn't take the I didn't take the smallest. I took this one, that's 62. This one would correspond to 2 qubits geometry, which are quadrangular over the 2. I take this one, that would correspond to 3 qubit geometry. Symplectic polar space W52. So, you can, from these two groups, the G and the H, you arrive at a permutation group on 2 generators that is of this order, and it turns out it's also a group of the very group of the E7 geometry, E7 group, the very group of the E7D group prime. So, and this is what one can get, the number of black points, the number of white points, the number of faces, and this is of genus 1, in this case. And you could also, it's also easy to find the cycle of the corresponding descent enfant. I didn't comment too much before, just to show you that you can get them. And you arrive at a graph, a collinear equity graph, with a given spectrum. It turns out that there are here three eigenvalues, that it is a so-called strongly regular graph that you can find in the table, in the list of graphs I mentioned at the very beginning. You can recognize the graph in this case. And you can also see that there are 135 maximum clicks of size 7, corresponding to this symplectic polar space and to the geometry of free qubits. So I gave you the example of geometry that is obtained. You see, now we start from the table, financial representation, and you build the corresponding symplectic polar space. This I talked about yesterday. I don't need to do it again. There are some interesting geometry with some interesting properties. So now I take another representation. Go back. I was talking about this one, now I'm talking about this one. But I was talking about this one, and below I've said this was for 3 qubits, symplectic polar space. So this one would be for 2 qubits, and I'm saying this one is for 2 qubits. If you take the representation in the atlas, you have this G. And they give you several subgroups of finite index, and I selected a few of them. The smallest one is that of index 27. You can create a descent of this signature, number of black points, white points, faces, a genus. You can stabilize this geometry, which is the geometry of the general quadrangle 2-4, that is line with 3 points and 5 lines through points. And the number of lines cut off by the triangle are 45. But I could select another index. I select this index, this is the corresponding signature, and it stabilizes another type of a geometry. It's an orthogonal array in this case. Now if I select index 40, I have a general quadrangle of order 3, which corresponds to the 2Q-treat physics. And there is another representation of order 40, which corresponds to the dual of this object. But you see the signature is not the same. It's a way to recognize the two. Or you can take this index and correspond to the dual of the first one. You see the table this table is some type of finite representation very useful because essentially it gives you all interesting cases selecting the right index. Well, I was talking about this, and I am interested by the physics aspects. That's why I selected this index, the index 40, the number of lines of the number of points and the number of lines as well of the corresponding geometry of 2 qubits. But now you can say, what about the others? They are in the table. have their physical significance? And this is more or less right. Only this one has no significance. The SP45 would correspond to two 5-Ds. And if you want to have the corresponding quantum operator, it's not too easy to do the calculation, but if you use this methodology, starting from the representation in the atlas, you can create the corresponding quantum. And the same for free Q3, free 5-Ds, and so on. For example, the case of this case in red, for Q-treat, this is the symplectic polar space, and this is already a quite big object. I didn't mention the index in this case. That's quite high. For example, for this case, this is my footnote 5. Where is it? For this case, my footnote 6, the index is more than 3,000. You see, imagine a graph with more than 3,000 vertices. This is the signature. Look, the genus is high, 226. These are the cycles. You can say a lot of things about a complicated object. For this case, corresponding to two 5-Ds, you would have there are two. You can create two objects of index 156 with different signature and cycles. It turns out that the two ones are isospectral. But their structure in terms of the corresponding descendant form is different. So this was for the symplectic groups. Now remember, from the beginning there are different types of groups, and now I'm talking about unitary groups. The notation U means PSU. That is the projective special unitary group abbreviation. So one can ask, I already showed this slide yesterday, so that I don't need to spend too much time. You have all this group. Can we recognize something that to that correspond to general hexagon for the two? That was a good way of putting the 3 qubits, remember? Due to this isomorphism between due to this equality between the unitary group for 2 and SP group for 3, this is corresponds to GQ to Q-treat. And there are other cases, and I've already said that they are corresponding to interesting near polygons.
This is because it's not short.
My battery is low.
It's
Maybe there is no power. This. Is there a power? Yes, but I think it's in the battery. They should be, I've not checked the one. I think it's not. Now I can check it. See. No, It's not charging. Maybe one can try the other.
No, this one. Maybe it was not. Okay.
Okay, this is the... Okay, this was about unitary groups. So that as you saw, for the symplectic group there is much physics, for the unitary groups there is less. But maybe there will be physics, but it's just not recognized that all is a general quadrangle or a near hexagon play a role in physics. I don't know. So now, for the list of classical groups, the orthogonal groups. Now these orthogonal groups correspond to the physics of multiple qubits as well, but I'm talking about the dual graphs. I mentioned the dual graphs. What were the dual graphs? I said on the first day that instead of taking as vertices the number of observables and as edge or line the maximum committing set of observables, now I take as vertices the maximum committing set of observables, and if they intersect, then I put an edge, otherwise I don't. And this is what I call the dual graph. And it turns out that these dual graphs have a representation in terms of the orthogonal groups. 073 correspond to the 3 qubit, or 8 plus 2 correspond to 3 qubits, here for 3 qubits, 4 qubits, and so on. And now what is the geometry of this object? The geometry of this object are PGs. In fact, they are not. These are partial geometry. They are still not. They are still partial spaces, but they are not on the near polygon type. They are of the so-called partial geometry type, in the sense that again they are going in order. ST, S plus 1 point on a line, T plus 1 line on a point, and the alpha correspond to the incidence number of, in fact you have a line, you have a line and you have a point, and this is called an anti-flag, and how many lines are going from this point, how many lines are going through the line. And this is precisely the meaning of this alpha, the incidence number. This type of geometry have been recognized. They are called partial geometry. So as you see, all these cases are partial geometry, and the physical meaning is that of the dual graph the dual graphs in multiple qubits. So I finished for this section. I'll show you another aspect. It's one of my last paper. My main question is to know what is contextuality at the geometrical level. So as said, one can recognize contextuality in finite geometry as the impossibility to have the commutation of cosets reflecting all the lines, or all the edges of the graph, or all the lines of the geometry. This is my definition of geometrical contextuality. But still, I would like to have more, to really better grasp this concept. Is there some sort of kernel of the geometrical contextuality? And we are very happy that there exists a theory where maybe this kernel is present. And this is the theory, a theory due to a group theoretical people that are called McLachlan and Martin. There is a book by McLachlan, The Non-Compact Arithmetic General Triangle. No. Okay, there is a book, this is just the title of a section of the book that has relevance to us. I will show that we can start from the so-called Kleinian groups that are groups that act on the nuclear space. We already had a talk by Professor Zainuddin about the nuclear plane and the groups behind, but there is also a nuclear space. And there, the groups are of the form, the groups are so-called Kleinian groups, and they correspond to the, and they are the type PSL. No, they are elements. The element of the group of the form f of z equal a z plus b plus c z plus d, with the determinant a d minus b is equal 1, and a b c d are complex numbers. The way these are the elements of the group that act on the Euclid space. So, and there are subgroups of this group, but there are infinitely many subgroups. There are subgroups of a special type that are non-compact, arithmetic, and defined by only two elliptic generators. I will be more precise. And precisely this object I am interested in now. Now, at the geometrical level, when one takes the quotient of the Euclid space by the corresponding Kleinian group, one arrives at the idea that is an orbifold, a generalization of manifold. So what is a Kleinian group? Kleinian group, as I said, it's a group whose elements are in PSL2 or C that correspond to orientation preserving isometries of the three-dimensional space, Euclid space. And now a non-compact group is such that the corresponding orbifold is quotient by the group is non-compact. Then comes the idea of arithmeticity of the group. I don't want to give too much detail about that, but it is defined as the commensurability of the group of units of an order of a Cartesian algebra ramified at all real places over a number of fields. So it's quite a difficult thing, but it can be defined. What means arithmetic can be defined. This is mathematical definition. Maybe it's easier to understand that these groups can have only finitely many. Can have only two generators, F and G. And it turns out that if the F and G are elliptic, then there are only finitely many two-generator Kleinian groups. So there are, as I said, there are 21 different classes of these Kleinian groups that are non-compact, arithmetic, and generated by two elliptic generators. And I selected a few of them. Another aspect, and this has to do with what was said by Professor about the what's the name of the professor? We have this talk about the elliptic function. And I have the question: do you have something special when the square root of minus d is such that d is 1 and 3? Not general. Because here, there is something special in the sense that this Kleinian group are, I don't define commensurability, but that means they have something to do with these Bianchi groups that are the groups mentioned by Professor Rakimov for d equal 1 and 3. I suspect that there is some special elliptic curves that correspond to these Bianchi groups, but I don't have the, I don't know how. So, but one can forget a little bit this and specialize on classes of the Michael-Schlag-Martin series. And first, I start with the this again. I start in this case of my first row in the table. And now I have a group G and a group H, subgroup H. But here the group G is again the same than before, a free group on two generators, and the group H is not anything. It's a group that is in the Michael-Schlag-Martin table. That is, you can see in the Michael-Schlag-Martin table that there are such a representation of the Kleinian group. Okay, this is the representation of the Kleinian group. Yeah, these are this is the representation of K4 class. So it's less general than the general case. The Kleinian group is still a group that has infinitely many elements, but I'm interested now by finite index subgroup of this group and see if they relate to the geometry I'm interested in. M in square, M in pentagram, general quadrant over the 2 for 2 qubits, and so on. Okay? Remember, the one I am interested, GQ21, which is the 3 by 3 grid. Okay? M in square, pentagram, GQ22, which is my 2 qubit object, maybe W, which is this symplectic polar space, maybe W52, which is the 3 qubit object, or maybe JH22, quadrangle for the 2, which is another way, and so on. I mentioned GH, general hexagon to 1, corresponding to this, GO to 1, and other things. This is my question. What kind of geometry are recognized? Can I filter a little bit? And it turns out that with this methodology, for example, in this case, you will never get this. You will never get this. you can get this. In fact, there is only a series of geometries that are recognized. But I'm quite happy because at least I can recover this one, which is the one related to the Grothendieck theorem. Okay, it's an hyperplane of that, as I explained also in my welcome space talk. And I also mentioned this one. So I'll show you how it works. So, for example, this representation of the McLachlan-Martin group of type 4 is like that, and I can find a subgroup of index 9. This is the corresponding descent enfant. And this is the geometry that is stabilized. In fact, it is this is the 3x3 grid union another 3x3 grid that is skewed to it. And I represented only the fact that the union of two grids that are skewed to each other. It's not yet the simple 3x3 grid, but I will get it later. So another example, you can get from the same class but with different index this geometry, which is the line graph of the Peterson graph. The Peterson graph plays a role in encoding the 3 qubits as well. So this is the line graph. Now this is in another class 19. One gets this descent enfant that you already know, because this is one which is quite unique, as I said, and the first one that exhibits geometrical contextuality. And depending on the stabilizer subgroup you choose, you create two grids, one which is non-contextual and one which is contextual. This is one I showed you yesterday. This is corresponding representation. Now in class 1, this will ask a question if you had I don't know your name, the first table. This object here, this is the descent enfant, this is the corresponding geometry that is stabilized. It's in fact, it's just a full it's a graph, complete graph on 6 elements. Every edge, every vertex is connected to all of these borders, corresponding representation. And in this case, we are talking about the modular group, at least a representation of a modular group with elements x and y of order 2 and 3, plus and an extra variation. And this corresponds to, that means you can now only talk about the geometry of like that, but you can talk about the geometry that exists in the UPM plane, the tiling of the UPM plane. And it corresponds to a congruent subgroup that is called gamma of 2 of index 6. And the Bailey function behind, I said, I didn't take too much time to talk about the Bailey function. I give a few examples. Here the Bailey function is precisely the J function. Remember, it was given by in the talk on elliptic curves as well. This is the J function, and this is explicit. This was your question. The cube of this is a modular invariant. And this is the picture of the tiling. So see, in that, when you have the modular group, it's quite interesting because you can encode either as the 1, 2, 3, 6, you can encode it either as edges of the descent enfant, or as vertices of the geometry, or as the tiles in the UPM plane. So another example in the same class 1, this case that I already showed, This is the design already shown as stabilizing the Mermin pentagram, which is contextual. So this, the black line are contextual, and it's the corresponding tiling in the guard plane. Again, K1, you can stabilize the general hexagon GH21, this one, the descent d'enfant, the geometry, the tiling, okay? And now, look at class K5, you stabilize this case, 0 to 1. I already gave this picture, I gave this picture. Now I give you the corresponding descent d'enfant. So I'm in the list of Coset representative. So this object I didn't yet mention. This is the so-called, it's a general polygon, general octagon of order 2-4. Three points on a line and 5 line flow points. This is the index, 1555. This is, it comes from a representation of the modular group so that you can, well, I didn't plot the descent enfant, that would be too difficult. But this is the list of, this is just a sketch of the permutation group, first generator, second generator. And this is the tiling of the overall plane. It can be done with the software Sage. I did not do it by hand. So, but for example, for this object, this is the corresponding permutation group that is obtained, which is the so-called Kitts group. This is the signature of the descent. You see, this is the genus. These are the cycles, and so on. It's an interesting object because it's considered not as a sporadic group, but close to sporadic groups. This slide, I will not comment them. Just wanted to show you that so we have an approach of geometrical contextuality, and we have something more, the idea of an ROBIFOR by using the Kleinian groups of a specific type, and with this object we can recover objects that have to do with Coset-Becker theorem. It's clear at this level. Well, now we have also more generalized thin polygons that until now don't play a role in the study of Coset-Becker theorem contextuality, but there is a good chance that they are important. And now I finish my talk by talking about another list in the Atlas of Finite Group representation, which is the list corresponding to sporadic groups. And I start with a sentence of well-known theoretical physicist, Dyson, that works in quantum electrodynamics. He has a sneaking hope, not supported by any facts or any evidence, that sometime in the 21st century, physicists will stumble upon the monster group, built in some unsuspected way into the structure of the universe. This is, of course, only wild speculation, almost certainly wrong. But who knows? So, and okay, it's monstrous chapter of finite groups. But it's quite nice if you go to this section of Wikipedia. You have this diagram. Here at the bottom you have the Mathieu groups. They were discovered in the 19th century, at the end of they were discovered in the 19th century, yes. About the same time where the Riemann hypothesis was formulated. It's interesting. And then other groups were discovered, and this culminated in the 70s with the finding of the so-called monster group, which has a dimension, which has cardinality about 10 to the 54, which would correspond to the mass of the non-universe in kilogram. And you have all this group, and they have such a relation between themselves, which is in fact that this is the maximal subgroup of the monster. The Conway group is the maximal subgroup, and this one is the maximal subgroup of this one, and so on. So they have a relation, and they are also so-called. Well, this is happy family, and there are also some parias that are nowhere. I am here about here. So maybe I have a paria. Or maybe I'm not in the table. So this is like that. So I will be very brief about that. There is a monster group which is huge. And how to build this group is not easy. I would like, well, it's possible, in principle, it's possible to build it in terms of two permutation groups. But in that case, one would need 10 to the 20 points, this number. That means imagine you descend enfant with 10 to the 20 points. I would like to know how many black holes, how many black points, white points, genus, and so on. But it's difficult to know that. But you know that at least that you need this. You will need an index, a group of finite index 10 to the 20 of this of this group of two generators, free group of two generators. And otherwise, there is another way to build it from a so-called Greek algebra, whose dimension is this. So there is a very interesting observation due to Mac K, and people are working on that, the fact that there is a connection between the monster group and the J function I mentioned before. Strong connection between the two. And this can be expressed like that. It's possible to expand the J function like that, where Q is this thing, and the real part of tau is larger than 1. So this is one possible representation of the J function. And there are numbers of coefficients, C. And on the other hand, well, this is what I have at the left. And on the other hand, at the right, the number here appears in a different way as a in the characters, if you like, the Fourier decomposition of the monster group. Fourier decomposition, so-called character theory. This number appears in the Fourier decomposition of the group, and on the other hand, you see, you have the J function. They are, a priori, they are completely different objects. Not clear why they are. But you have this strange relation, and this is called moonshine. You know what moonshine is? Moonshine is a bad alcohol, see. Alcohol. Any alcohol, bad alcohol. This moonshine. So, and this moonshine phenomenon appears not only for the monster group, but also for the others, for some other sporadic groups. So, I recommend this reference. There are many things. I also wrote a paper already on that. You can find it on the archive. So, now, why I mentioned this, just because in the table there are these sporadic groups, in the atlas of finite group representation, there is this list, and also because one can play with descendant form. For example, in fact, I don't have the one slide is lacking in this version, but I have a slide where there are the descendant form for all these most of this group, except for the biggest ones. So the descendant form theory applies to this group as well. So I finished with this part. Then for people interested, I can give a fast show about how the calculations are performed in 10 minutes afterwards.